Hello, welcome back. In this video, we'll be looking at problem 109 from section 5.6 of the Larson Calculus text, 10th edition. This is a modification of problem 109. It is in section 5.6, which is about inverse trigonometric functions. We're asked to find the value of x naught that maximizes the angle between the line segment connecting 0, 2, and x naught 0, and the line segment connecting x equals 4, y equals 3, and x naught 0. We want to find the maximum value of the angle as well. So this is our picture. And here are our points. X equals, we have x naught, x equals 0, y equals 2. We have x equals 4, y equals 3. And then we have x equals x naught, y equals 0. So that's that point down there. And we're just trying to maximize the angle between these two orange line segments. So if I'm graphing them there, that's the first line segment, that's the second line segment, and we're trying to find to maximize that angle in between. Now, if we change the value of x naught, we move it from here to all the way to here, we can see that that angle between those two line segments changes. Now, I've actually graphed that function here. This is the angle between the two orange line segments, and we want to find the maximum. We can just tell by looking at the graph that it's somewhere around here, and I think it's actually like almost exactly that 2.0995 value. I'm sorry, I accidentally left that on the screen. Let me hide that from you, and then we'll actually derive that together. So this is our graph, or excuse me, our image of those two line segments. We can change the value of x naught. Now, if we want to, we can let our x naught values go beyond the interval from 0 to 4. And it looks like I've done that here. I let x naught go between -2 and 6. But I think we can all see that that x value gets, or that angle gets smaller and smaller once we're outside of the interval from 0 to 4. You see how small it is? We see that the maximum has to be somewhere in between 0 and 4. Intuitively, that makes sense. And I think that that maximum is at about that value, which is a point I accidentally plotted and forgot to hide from you before I created this video, excuse me. All right, so we're trying to maximize that function, or maximize that angle between the two orange line segments. Now, if we want to find that maximum angle, we can do so by sort of thinking about two right triangles, one to the left of this orange line segment on the left, and one to the right of the orange line segment on the right. Now, when I look at that right triangle, I'm thinking of the right triangle created by the positive y-axis, the positive x-axis, and that orange line segment. So I guess we could graph it. We could say, let's let y or x equals 0. And I'm only interested in the x values, or x equals 0 between y equals 0 and 2. So that's one boundary. That white line segment is 2 units long. And then we'll have x equals x naught, or excuse me, y equals 0, excuse me, on the interval from x equals 0 to x naught. And so we've got that triangle right there. So that is our x value. That's a teal line segment. Now the angle between that orange line segment and the teal line segment, we could call that theta 1. Now theta sub 1 satisfies the following. It's equal, or the tangent of theta sub 1 is the opposite side, or the side opposite of theta sub 1, divided by the adjacent side relative to theta sub 1. And the hypotenuse is always opposite the 90-degree angle. So the hypotenuse is that orange side length. So we know that the tangent of theta sub 1 is that 2, because that's the length of the side opposite theta sub 1, divided by this length of this teal side, which is x. Now, if I take the inverse tangent of both sides and require that our x value is between 0 and 4, then we know that our theta value is always between 0 and 90 degrees or 0 and pi over 2 radians. So we can just use right triangle trig and we'll take the arctangent of both sides to get theta by itself. So if the tangent of theta is 2 divided by x, then the arctangent of x, or of 2 divided by x, is equal to our theta value. Now, that is theta, but we might prefer, rather than having this 2 divided by x inside, we might prefer to have the x in the numerator. We can have the x in the numerator if instead of using opposite over adjacent, we use adjacent over opposite. If we use adjacent over opposite, we should use the cotangent function, because then we're talking about the cotangent of theta 1. That is the adjacent side over the opposite side. So that'll give us an x divided by 2. So that's theta 1. And then for theta 2, that's that right triangle to the right of this point that's created by the line segment given by x equals 4 for y between 0 and 3, and then the distance between this point x naught and 4, which has a length of 4 minus x naught. Or in terms of x, if we call this is the x coordinate of this purple point x, this distance from 4 to that x value is called 4 minus x. So I'll call that theta sub 2. And maybe we should graph that as well. Let's graph the triangle. I'm going to use teal for that triangle on the left. And let's use purple for the triangle on the right. So I want x equals 4 for x or y between 0 and 3. So we know that that purple line segment has a length of 3. And then we'll have a y equals 0. But we don't want all of y equals 0. We only want the part of y equals 0 for x between x naught and 4 minus x naught. Is that okay? It's giving us some problems, isn't it? What is my x naught value right now? 2.32. So I want my x to be between 2.32 and 4 minus 2.32. I see that when we can't quite do that, because if I have x naught greater than 2, then this 4 minus x naught is going to be larger than that. I'm sorry. The upper bound is just 4. So x starts at x naught and ends at 4. So the length of the line segment is 4 minus x naught. Sorry about that. I hope that makes sense now. So we've got y equals 0 on this interval, which has and we've got a line segment there. That white line segment has a length of the left or the rightmost x value minus the leftmost x value. So it's 4 minus the x. And then the side opposite the angle that is made by this orange line segment, the angle between the orange line segment and the white line segment, the side opposite that is the length of this purple side, which is 3. So I can use the arc cotangent again. I'll use, we know that the cotangent of theta sub 2, where theta sub 2 is that angle between the orange line segment and that white line segment, is the arc cotangent of the adjacent side, which is 4 minus x, divided by the opposite side, which is 3. And I don't want to graph that. I just want to write that down. So that means the angle that we're interested in, that's the angle between the two orange line segments, sort of represented by the angle in that teal region. That is 180 minus theta sub 1 minus theta sub 2. If we want, we can change that side length to a purple one so that we can see those two right triangles if we want to. So our y value, or the angle that we're looking for, is pi, or 180 degrees, minus theta sub 1 minus theta sub 2, and theta sub 1 was arc cotangent of x divided by 2, and theta sub 2 is arc cotangent of 4 minus x divided by 3. And then we say, okay, I want to graph that, but only on the interval from 0 to 4, because we know that that angle is going to be maximized between 0 and 4. If you want to, you can graph the entire thing, and then you could let your x values change. You could let your x value take on any value between negative infinity and infinity, because that arc cotangent is defined for negative infinity to infinity. But we know that the x values that we're interested in, the ones that are going to maximize the function, are between 0 and 4. Say, okay, well then what is the x, or what is that angle measure at a particular x value? Well, we can plot that point, x naught, and our theta value in radian measure, and plot it that way. And then we see when x is equal to 1.83, the angle is approximately 1.36726. If we want that value in degrees rather than radians, we multiply by 180 degrees divided by pi radians. We see 180 divided by pi is about 57.3. So that just tells us that there are 57.3 degrees in 1 radian, 57.3 degrees per radian. So if you see 1.36 radians and you're like, I'm not really sure what that angle is, just multiply by 57 or 58, and that'll give you the angle in degree measure. I think we all have a better intuitive sense for angles in degree measure as opposed to radian measure, but I might be wrong. There might be some people out there that are really comfortable with radians. But that y value is in radians. That's our theta value. And we see at x naught equals 1.83, the angle is approximately 78.34 degrees. And if we change our x value, we get different y values. Now I've defined my theta in degrees, in terms of theta in radians, and I've required that my x be between negative or 0 and 4. So when I try to go outside of that range, or out of that interval of x values, that domain, it says theta in degrees is undefined, but we could change that if we wanted to. We could do that instead. Let's make that one solid and that one dotted. Okay, so that's still our picture. And now if I allow myself to change the x naught, where my x naught is outside of the interval of values, because I changed the definition of that theta in radians, it's actually giving me the angle. So we see that that angle when x equals negative 1.22 is approximately 28.7 degrees. And when x equals 5-ish, we see that that angle is approximately 0.87 radians, which is about 50 degrees. But the maximum of that angle seems to be somewhere around 2. You can see it, that it's somewhere in that vicinity. And as we move that x value from left to right, we see that the angle increases. It's a 55.5 there, continues to increase, continues to increase. Then I see a 78.7 at one point, and then it starts to decrease. And we're trying to maximize that angle. We're trying to find the x value that maximizes the angle and the maximum angle. So to do that, we use the chain rule to take the derivative. And we'll do that on paper. So we'll compute the derivative. The derivative of pi is 0, and then the derivative of arc cotangent is a -1. Let's write that rule down. divided by our input squared plus 1. So it's just -1 times the derivative of arc tangent. Now, when because I have a -1 factor here, that -1 times that -1 is going to give us a +1, and we'll have to use the chain rule. So I have the negative arc cotangent of a function. The derivative of the negative arc cotangent of a function is +1 divided by that inside function squared plus 1. Then put the inside function back inside. And then we multiply by the derivative of the inside by the chain rule. The derivative of x divided by 2 is the same as the derivative of 1/2 x. So we get a 1/2 as a factor there. Now, if I'm trying to simplify this, I would square the numerator and square the denominator. So I'd have a 4 in the denominator of a fraction that is in the denominator of a larger fraction. You might say, I don't like having that 4 in a denominator of a smaller fraction within a fraction. I'd like to get rid of that. Like, let's just have one fraction instead of fractions within fractions. In order to have one fraction instead of fractions within fractions, we want to clear that 4. In order to clear that 4, I need to multiply by a 4. I've already got a 2 there, so I can multiply by 2 in order to get what I want. But I can't just multiply by 2 in the denominator. If I multiply by 2 in the denominator, I have to do the same thing in the numerator. That way I don't change the value of the fraction. So this is just multiplying by a well-chosen 1. It's going to have the same value, the fraction will. It'll just be written in a different form. And that is our theta prime for this term plus this term. Then we'll do the same thing for the negative arc cotangent of 4 minus x divided by 3. The derivative of a negative arc cotangent is a -1 times a -1, which is +1 divided by the inside function squared plus 1. We put the inside function back inside. And then we multiply by the derivative of the inside by the chain rule. Now, the derivative of this is the derivative of 1/3 times the quantity 4 minus x. The derivative of 1/3 times some function is 1/3 times that function. And then we multiply by the derivative of 4 minus x, which is just -1. So I'll put that -1 in the numerator. And again, if I square this numerator and denominator, I have 4 minus x quantity squared divided by 3 squared, which is 9. Like to clear that 9 in the denominator of the larger, of that smaller fraction within the larger fraction. So I want to multiply this by 9. I'm already multiplying by 3, so I'll just multiply by an extra 3 in order to multiply by 9. But I can't just multiply the denominator by 3 because then it would be 1/3 the size it was before. I need to multiply the numerator and denominator by 3 so that I don't change the value of the fraction. And we do that, we'll have a 3 over 9 here, and we distribute that 9 to this term and this term, and that 9 will cancel, and we will no longer have that fraction within the larger fraction. So that's our theta prime. We just need to simplify it. In the numerator, we have 1 times 1 times 2, which is 2. Divided by, we have x squared over 4 plus 1, all multiplied by 2 times 2, which is 4. And here we've got a -1 times 3, which is -3, all divided by 4 minus x. Actually, let's square that. Square the numerator and square the denominator. Add 1. And then multiply that by 3 times 3, so that's 9. Now, when you distribute the 4 here, the 4's will be cleared there, and you'll have 2 divided by x squared plus 4. And if you distribute the 9 there, we'll have -3 divided by 4 minus x squared plus 1. Now, we want to set this equal to 0 and solve for x. Now, in order to do that, we need a common denominator. The least common denominator of two fractions that have nothing in common, no common factors in their denominator, is just the product of their denominators. So the LCD will be this denominator times that denominator. So what you do if you want to add those two fractions together or subtract those two fractions is you identify the LCD. So that's x squared plus 4 times the quantity 4 minus x, quantity squared plus 1. Oops, that should be a 9. Distributed a 9 there. And then you say, okay, this times this is my LCD. What is missing from this denominator to get my LCD? Well, I've already got the x squared plus 4, so I'm just missing this 4 minus x quantity squared plus 9. So we're going to multiply the numerator and denominator by that 4 minus x quantity squared plus 9. Again, doing that to the numerator and denominator does not change the value of the fraction, just writes it in a different form. And here, we've already got this factor, we're missing the x squared plus 4 factor. So we multiply the numerator and denominator by x squared plus 4. And that will allow us to have a common denominator. And since we have a common denominator, we'll be able to add the numerators, keep the common denominator, and that'll be our theta prime. So if I distribute this 2 to this expression here, I have 2 times the quantity, 4 minus x squared, plus 2 times 9, which is 18, minus 3x squared, and negative 3 times 4 is negative 12. We're taking all of that and we're dividing by the LCD. Now this 4 minus x quantity squared, if we square it, we'll have 4 times 4 is 16. Outer times outer would be 4 times negative x, so negative 4x. Inner times inner will also be a negative 4x, so we'll have a negative 8x. And last times last, if we wrote that twice and FOILed, would be x squared. 18 minus 12 is 6. Then if we distribute the 2, we'll have 32 minus 16x plus 2x squared plus 6 minus 3x squared, all divided by x squared plus 4 times the quantity 4 minus x squared plus 9. And then we'll collect like terms. 2x squared minus 3x squared is negative x squared. Then we have negative 16x. And then 32 plus 6 is 38. Now, we want to find the maximum value of this function. In order to find a maximum, we find the critical points first. So we look for those x values where the derivative is 0 or where the derivative is undefined. When we look at this fraction, we say the derivative is always well-defined because x squared plus 4 is always greater than or equal to 4 because I'm taking something non-negative and I'm adding 4 to it. And then the same thing is true here. I've got something non-negative. 4 minus x squared is always greater than or equal to 0. If I add 9 to it, that result is always greater than or equal to 9. So this is a positive number times a positive number. So this is well-defined all the time. So we don't have any critical points where theta prime is undefined. But we might have a critical point where theta prime is equal to 0. So theta prime would equal 0 when the numerator is 0 and the denominator is non-zero. And the denominator is always non-zero, so we're only concerned about that numerator being 0. Now, in order to figure out the x values that cause this equation to be 0, you can use a quadratic formula, you can complete the square. There are lots of things that you can do. I would prefer to complete the square. In order to simplify this, rather than factoring out a -1 and simplifying from there, I think I'm just going to multiply both sides by -1. So multiply by -1, then we'll have x squared plus 16 minus 38 equals 0 times -1, which is 0. And then if we add 38 to both sides, this is what we get. Now to complete the square, we take half of this number. Usually we call that b. So b is going to be 16. Take half of that. That's 8, and then square it. That's what you add to that side to have a perfect square. We're going to add the same thing to both sides to keep everything nice and even. On the left-hand side, we can factor that. We're looking for two numbers that multiply to give us 64 that add to 16. They're always that at b over 2. It's going to be 8. So this is x plus 8 times x plus 8, or x plus 8 quantity squared equals 38 plus 64, which is 90 plus 12, which is 102. So we're trying to get x by itself, and we've got x in parentheses squared. We want to get rid of that squaring function. So to undo the squaring function, we take the square root. Don't forget your plus or minus on the right-hand side. Then we'll have x plus 8 equals plus or minus the square root of 102. And then to get x by itself, we'll subtract 8 from both sides. So x is equal to negative 8 plus or minus the square root of 102. And so you say, okay, what does that mean? Well, there are actually two values there. X equals negative 8 plus the square root of 102, and x equals negative 8 minus the square root of 102. Now we're only interested in the x values on the interval from 0 to 4. And the square root of 102 is just slightly larger than 10, right? So this is approximately negative 8 plus 10, which is approximately 2. And this is approximately negative 8 minus 10, which is approximately negative 18. This is the x value on the interval of interest, because that is going to be slightly larger than 2, which is between 0 and 4. Negative 18 is way outside our bounds, so we're not concerned about that. Okay, so this is our critical value on the interval of interest. Sort of our implied domain for this particular application. It's a geometric application of an optimization problem, algorithm, I guess, if you'd prefer. Optimization series of steps that finds us an optimum value. All right, so we've got theta prime is equal to this, and we know that theta prime is equal to 0 at this x value. And the question is, well, what is the sign of theta prime on the left and right of this particular x value? Well, to figure out the sign, SIGN sign of theta prime on that interval, we make a sign chart, and we restrict ourselves to the interval from 0 to 4. And we'll look at x equals 8, negative 8 plus the square root of 102, which is approximately 2. That's on the interval. And we see that theta prime is this function divided by this function times this function. The product in the denominator, I'm just going to write denominator, is always positive. So it doesn't matter which interval we're on, that denominator is always positive. But that numerator is sometimes positive and sometimes negative. We see that if we complete the square here, actually, let me just say the numerator is equal to this. This is what we get if we factor out the negative 1. We have that. If we take half of 16 and square it, that's 8 squared is 64. We can add that 64 in the parentheses as long as we also compensate for that. Now, be careful, adding 64 in the parentheses actually added negative 1 times 64, or added a negative 64 to the numerator. To compensate for adding a negative 64, we have to add a positive 64. I know it doesn't look like adding a well-chosen 0, but we actually did add a well-chosen 0 because of that negative 1. We've got a negative 1 times 64 that we were adding. So to compensate for adding negative 1 times 64, we need to add positive 1 times 64 to compensate. So the numerator is actually negative 1 times x plus 8 squared plus 102. And that is just an upside down parabola. And the graph of that looks like this. And we know that the roots are approximately 2 and negative 18. So at 2 and negative 18, the graph looks like that. And like, what's halfway in between 2 and negative 18? Add them, we get negative 16. Divide by 2, we get negative 8. Well, of course, negative 8. I don't know why I didn't think of that. The corresponding y value at x equals negative 8 is 102. So roughly, the graph is going to look like this. And we're really only interested in the graph on this interval from 0 to 2. So this is our function. That's not the whole derivative, but it's just the numerator of the derivative, and the numerator of the derivative changes or determines the sign of the derivative because the denominator is always positive. Say, okay, if I'm to the right of the 0, this is not 2, but it's approximately 2, right? And if I'm to, the left of that 0, the y values on the graph are positive. So let's say numerator is positive to the left of the 0 and negative to the right of the 0. So we have a positive times or positive divided by a positive, which is positive, and then we have a negative divided by a positive, which is negative. So the function goes from increasing to having a zero slope to decreasing. So we've got a relative max at that x value. So theta evaluated at -8 plus the square root of 102 is a relative max by the first derivative test. And if we want that maximum angle, we have to substitute this x value into this function. And then when we do that, we'll find the maximum angle. And we'll use the calculator to get a numerical approximation of that -8 plus the square root of 102. All right, so we want to, rather than doing everything that we just did on paper, we could just graph the function, graph theta prime. That's what it looks like after we simplify it. And we can see that theta prime goes from positive to 0 to negative at approximately 2.07, it looks like. It's bizarre. Yeah, that's not quite the x value that we're looking for. We said if you set theta prime equal to 0 and solve for x, you get -8 plus the square root of 102, which is this 2.0995. And then we have -8 minus the square root of 102, which is that -18-ish number. The one on the interval is that 2.0995. So we'll evaluate the derivative there. And then we'll find the theta value in radians, which is that 1.37427. Oops, actually, still plotting the x naught. Don't want that one. I want it to plot this point for me. Not the derivative, the original function. Oops, I need to use that subscript radians. At that x value, our theta value is 1.37435 radians. If we want that in degree measure, we multiply by 180 degrees divided by pi radians, and we get 78.7 degrees as our angle. So that's one way of doing that. Now, again, alternatively, rather than using the graph of theta prime, we could use the graph of that parabola that I mentioned. We had y equals 102 minus x plus 8 squared. It was written in a slightly different order before. This is what it looks like. And we want to make sure our range includes the y value. And let's go from -20 to 3. So the graph looks like that. Well, we know that that parabola has a vertex at x equals -8, y equals 102 from our studies of precalculus. And we know that the function is 0. Let's call this f of x. We know that the function is 0 when x equals -8 plus or minus the square root of 2. So we'll have -8 plus the square root of 102. I think I may have said that wrong. And then we would evaluate our function there. Or do the same thing, but instead of adding the square root of 102, we can subtract square root of 102. Evaluate our function there. And then we say we're not actually interested in the whole function. We're only interested in part of it. So let's make this a dotted line and say, I want the part of the graph where y is equal to this function, but I want my x values to be between 0 and 4. That's what I'm interested in. Then I go over here. So I say on the interval from 0 to 4, what happens at that relative minimum? Or excuse me, what happens at that 0 point? Well, the derivative or that quadratic function goes from positive to 0 to negative. And that is in the numerator of our derivative, theta prime of x. And the denominator is always positive. So the sign of theta prime is determined by the sign of this function. And this function is positive between 0 and the root, and negative between that root and 4. So the original function goes from increasing to having a 0 slope to decreasing, which is exactly what we see when we look at the graph of just theta prime itself. So that is how we do that. I think that's it. So we were able to find the maximum value of the angle. That's 1.37 radians, which is approximately 78 degrees, right? 78.74 degrees. And that occurs at x equals 0.2995. It's that point between these two, or on the x-axis, that gives us that maximum angle here.